Okay, so I am already in the part wherein I have accomplished how many stages? One, two, three, four, 5, 6, 7, 8 stages. So I have created the tie line here, and then my task is I have also extended the operating line from this point up to this point. So this is the latest operating line I created. Okay. The next thing that we're going to do is to continue. Okay, I'm going to extend another guideline over here, vertical line. Okay, okay, here, vertical, and then create another horizontal, and then another vertical. Okay. Notice that your your value of the composition of your x crossed already the feed line. So which means that our tie line, okay, I will be copying a violet colored, our tie line for this one will be starting from this value here and here. Okay, so if you notice, that this tie line over here, this is the 1, 2, 3, 4, 5, 6, 7, 8, ninth. The ninth tie line, which corresponds to the ninth stage, already intersected the feed line. That means that the ninth stage is your feed stage, or this is the stage wherein the feed was introduced. Okay, so now it's a very important portion over here because we're going to transition to a different to another difference point. Okay, so remember that this is the delta E is called the difference point in the enriching section. Since we have crossed over the feed line, we're going to move into the delta S. Okay, so I will be copying, okay, this one, copy, and then paste it there at the bottom part. KB, and change it to delta S. Okay. If you notice, I have deleted the delta E min and delta S min line because I find it disturbing. Not really disturbing. I find it annoying when I started doing the stepping off. So we are going to use the delta S to pivot and look for the concentration values. Sorry, for the equilibrium concentrations in the vapor phase. Okay, so that's the most important thing that you have to take note, that if you were able to cross over the feed line, okay, you have to, okay, what will you do for this one? You have to create an operating line that will touch this point and touch this point over here, and then extrapolate that operating line to a certain point wherein you will touch the blue line over here. So okay, to further demonstrate what I mean by that, okay, let's create a new line because this is a new operating line. Okay, I will just be extending it here, extend, and then touch, okay, this portion over here. Okay, touch this one. Okay, until such time, okay, it's a little difficult because you can see it clearly. Let's zoom it out. Okay, we have to touch, okay, this one here. Okay, so the approach in the stripping section will be different because yeah, because we need to extend from the delta S up to this line over here. So let's change the color to What color do you want? I think it should be something that is darker. Violet. Oh, we have already green. We can just use pink. Let's just use violet. I know we have already violet for this one. I find it too dark. Okay, I'm very sorry for being undecisive. This one. If I increase the weight, yeah, but it's too bright. Okay, let's just use this one. That will be our operating line. Okay, I find it too thick. Just 1 point. And then after that, okay, remember that we did this because we need to extend that operating line to hit this point. So we're going to extend again. Let's do the same thing again. Okay, the extension of the guidelines towards the tie line won't really change. Okay, they won't really matter here. Touch that point, and then you continue doing it over and over again. But what made it different is the fact that you won't be anymore using delta E, but you're going to pivot to the delta S. Okay, there. And then, once you found that point already, okay, create the operating line. Okay, so what you're going to do is to there, extend, and then touch that point. Alright. Was I able to make the tie line already for this one? Let me see. Tie line. Touch. Oh, I wasn't able to create the tie line for this one yet. Okay, apologies. Here. I think I should have used a brighter color for the stages. There. And then you have to touch the operating line here. Okay. And then once you touch the operating line here, this one we're going to create a guideline here. So it really takes a long time. It actually depends on the problem. Okay, so not all problems are as difficult or as lengthy as this one. Okay, touch it here in the equilibrium line, and then oops, extend here, and then let's make a tie line. Yeah, I think the process is to extend, make the tie line first before you make the operating line. Alright, and then extend it, okay, in the difference point. Okay, so yeah, the point where you're going to stop is the point that you will be crossing over this line over here. Okay, so that's a very important step. So you will stop doing the step off. It's not really called step off because you don't really step downwards, but yeah, let's just call it that way. Let's extend this one. Okay, your goal is to the only time that you're going to stop is if you are going to exceed or to go beyond this line over here in the bottoms. Okay, just like what you did in your McCabe feel. Okay, extend downwards. So it's kind of lengthy, guys. Yeah, but that's the part of the academic, you know, challenge in studying Ponchon-Savarit. Yeah, and after that, create tie line again. Okay, I don't know when I'm gonna stop. Okay, there. And then create another operating line. Notice that it becomes, broader. Yeah, broader in a sense that, um, yeah, here they're too, you know, they're too cramped. So it takes forever. It looks like as if it takes forever to finish. But we are going to finish it, guys. Okay, so I'll cut this video and then proceed to the part where I'm done with stepping off. Okay. Okay, so I continued the stepping off, and I'm already at this point wherein I did my operating line, my last operating line. Okay, did my extension of the guidelines going down, and then extended here, and then went up. Okay, so this will be my last tie line for the stepping off. Okay, so why did I say that it's my last tie line? It's because this tie line over here already intersected with the vertical light orange line that I placed here. So that indicates that this will be my last stage to achieve um, the desired bottoms product. Okay, so let's count. Okay, so let's count the violet ones. Those are the relevant lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, we have 17 stages, and as for the number of trays, the 17th stage is counted as a reboiler, so it's not a part of the tray. So the number of trays here is only 16. Okay, so 17 stages but 16 trays plus 1 reboiler. Okay, so we're done with the Ponchon-Savarit method, the stepping off process. Okay, so let's go to that part. Okay, yeah, the next part will be to solve for the condenser and reboiler heat duties based on the formulas for Ponchon-Savarit method. Okay, so there are actually formulas that were these formulas were already presented in the derivation part. So it is expected that if you underwent the entire derivation of the Ponchon-Savarit technique, you have already encountered these formulas by yourself. Okay, if not, then you have to just live with the fact that, okay, these are the formulas and you're going to use this to determine the condenser and reboiler duties. So the condenser duty, okay, the symbol for the condenser duty is QC. Okay, well, the reboiler duty, okay, these are the amounts of heat removed and added by the condenser and reboilers respectively, okay, to achieve the desired flow of heat and achieve the desired concentration of the distillate and bottoms. Okay, the reboiler duty is QR. Okay, there are actually relationships as to how we're going to deal with this one. Relationship between the values we can read off in the Ponchon-Savarit diagram and the values of QC. So let's go over the first equation relating the value of Q prime to the value of QC. Plus D. Okay. So remember Q prime? Q prime is the Y value of your delta E. Okay. So since you have already the value of Q prime, which is 75,500, okay, and then the value of can I just use this value over here, the value that I used in my calculations, because this is the one I used to get the value of my QC. 523.52 kilojoules per kilomole. You also already know the value of your HD, right? Your HD value is here 227.27. 227.27. And then the value of your D is, what's this? Your distillate is 54.26 kilomoles per hour. 54.26 kilomoles. This is kilomoles, sorry. Kilomoles per hour. Okay. And then, yeah, just substitute this one to determine the value of QC. So to do this, so you have Q prime minus HD multiplied by your D to get the value of your QC. Okay. So if, please calculate this on your own. Okay. So the value I got here is, I'd like to check first if I'm doing it correctly. Is the formula correct? HD HD plus QC. Okay, HD plus QC. Okay, so the value that I was able to get is my HD correct? It's 227 point, yeah, and then the value of my 6, okay, yeah, that's correct. So the value of my QC is equal to, okay, for a while, okay, this one, 3,526,900 kilojoules per hour. Usually, condenser duties are reported as kilojoules per second or kilowatts. So let's convert the 1 hour to 3,600 seconds. So to get the answer of 979.69 kilowatts. These are my answers. It will really depend on your readings in the graph. Okay. For my, this is the first relationship that you have to take note, relating Q prime and QC. Okay, the value of the next relationship is this one. Q double prime equals HB minus QRB. Okay, there might be some new terms to you. Okay, the Q double prime is the y coordinate of your of your delta S. Okay, so if you want to know for the y double prime, just go to this point over here and then read off the y coordinate. That's the y double prime. Okay, my y double prime value, according to my reading here, okay, for a while, this is equal to HB minus QRB. Okay, this is equal to negative 82,272. Negative 82,272.73 kilojoules per kilomole. Okay, and then HB. How do you get the HB? HB is actually located here, guys. Okay, I was not able to present it earlier. I'll just use this line over here to locate HB. HB is here, this one. Just read off the value of your HB. Okay, let's put it here. Just go to the saturated liquid for HB, then extend it horizontally so that you will read the value of your HB, the enthalpy of your bottoms product. HB, okay. My HB reading is equal to 4,545.45 kilojoules per mole. And then yeah, you can actually solve for that one. You have already the bottom's value, which is equal to 45.74. 45.74 kilomoles per hour. And then yeah, solve for the value of QR. So this will be Q double prime minus HB equals negative QR over B. So multiply both sides by negative 1. So you're going to have HB minus Q double prime equals QRB. So to get for QR equals B times HB minus Q double prime. Yeah, my answer for this one is, okay, 3971.063.55. This is kilojoules per hour, and then multiplied by 1 hour, 3,600 seconds. That is 1103.07 kilowatts. Okay. Yeah, so those are my condenser and reboiler duties. Okay. So we're done with that one. The last item is on total reflux. Okay, finished. Okay, I think this is the easiest part. Make another Ponchon-Savarit method to determine the minimum number of theoretical trays at total reflux. Okay, take note that when you are going to do minimum number of theoretical trays at total reflux, take note that the operating lines at total reflux are vertical, which means no more delta E. Oops. Yeah, no more delta E and delta S. Okay, so it's easier. Okay, let's copy the, oops. Okay, no more delta E and delta S. Okay, let's just paste it here and then let's change it as. Okay, no more delta E and delta S. So how are we going to do that? Okay, so I will okay, so to do that, okay, I'll cut the video and then connect it to the part where I will be demonstrating. Okay, so continuing my discussion on the total reflux. So I have prepared another Ponchon-Savarit diagram to which I can do the total reflux stepping off. So I have marked the feed point, the distillate point, and the bottoms point in the HXY diagram. And then I created some lines over here to indicate the starting point and the ending point of my stepping off. So again, we do the same thing. It's really the same. Okay. Uh, for the part wherein we're going to create the tie line. Okay, that's the similar part. Okay, so why can't I create a tie line or create a guiding line? here. So touch it to the 45-degree line first. Okay, and then extend it to the equilibrium line, and then go vertical there. Okay, remember that we are creating the tie line by connecting this one over here and this one over here. Okay, so I think the color, let's change the color to red. Okay, just to make something it brighter. Okay. Okay, now before there is we have a delta E, to uh, we are going to create an operating line by connecting the dot or the point here and then towards the delta E. But for total reflux, the delta E is infinite, so our operating lines are all straight vertical. So that means my operating line here is just a oops. My operating line here is, apologies. My operating line is here. Okay, for a while. Okay. I think I have a difficult time in clicking the arrows. Okay, why is it so hard to click the arrows? To click the lines. So I'm going to create a straight operating line starting from this one to this one. Okay, and then extend it. And then I'm done. Okay, the next thing to do is what? To extend again that line. Okay, yeah, the next thing that we're going to do is create what we did in the previous problem in the previous subsection is we started here up to there, right? But it's already a straight line in itself, so you don't need to start here to create the guide for the tie line. You can just start here at the bottom part. Okay, continue what it started here and then extend, okay, toward the 45-degree line and then extend toward here. Okay, it's kinda easier there. And then create a tie line. Okay, just copy paste. Okay, connect. Okay, and then create an operating line. Okay, why is it there a problem with the operating line? Okay, straight operating line, just make sure that it's straight. Okay, there. And then continue making the line going down and then connect it again here horizontally to the equilibrium line. Then go up and then create a tie line again. Okay, create a tie line. And then next is to make an operating line. So you repeat the same process again and again to determine the to determine the number of stages of total reflux. So again, no need to start here because if you start here in making the guideline, you just follow that vertical line. So no need to do that. But instead, start from the bottom part of the line here. You can just copy the line what you did and then extend it downwards and then yeah, okay, follow through and then go up. Okay, in this part no more pivoting because the delta S point is also at infinity. Okay, so you just it's just like doing a stepping off in McCabe field for total reflux, right? And you just touch the edges of the equilibrium line You are also doing the same thing here. Oops. So create. Okay, let's continue this one. I will not cut anymore the video. I think it's doable. Okay, and then create the operating line. Okay, what happened? Okay, it moved. Okay, I'll make extra operating lines here. Okay, just to make sure. And then connect. There are really some lines that are so difficult to handle. And then extend it. Okay, connect this line over here and then go down. I just connected it because it's just there. But if you're going to use a pencil or ruler, I think you need to really, follow through the vertical line to for you to not get lost. Okay, don't it's not reliable to connect lines in that manner. So just use your ruler, start from here and then go down. Okay. Yeah, and then okay, tie line. After you create the tie line, then create an operating line. Okay. Okay, I think we're almost done. Oops. Okay. There, and then what else? Yeah, continue again. Okay, this is getting boring. Okay, but we need to push through. Okay, I don't want to cut the video. Um, I want to finish the video containing the correct answer. And continue. Yeah, it's just easy to follow through everything. Just make sure that everything is organized. Okay. Okay, and then connect. We're almost done. Okay, we can do this. Okay, so yeah. What makes everything so lengthy is the fact that I conducted it using Microsoft Word. So it's not ideal. And then create a tie line. Oops. We're almost there. Okay. Then connect it here. And then continue. I think this is the last step or last two steps, I think. This is for the minimum, for the total reflux. So total reflux corresponds to the minimum number of stages. Oops, I forgot to place the operating line. It really made me confused. Apologies. Yeah. And then, yeah, we're going to make another tie line. Oh, we're still going to make another one. We should not stop it here because we have not crossed over this line yet. Let's change the color of this one. Let's change it to black so that this will be or just violet. Okay, we need to cross that one. Cross over. Oops. Okay. Okay, there. And then last but not the least, okay, I'm done. Okay, so connect them, and then connect, connect. Oopsie. Okay, hooray. We're done, finally. So no more adding of operating lines because that's useless. So we just stop it here. There. And then there. We're done, finally. So let's now count the number of stages for the total reflux. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 theoretical stages, which means that it has 8 theoretical trays plus 1 reboiler at the bottom. Okay. So yeah, that ends my video for today. I hope you learned a lot of things about drawing Ponchon-Savarit diagrams. Okay, and answering questions related to continuous distillation design via Ponchon-Savarit method. Okay, that's it for today. Thank you so much and see you in my next Ask Teacher J videos. Goodbye.